So hello everyone. Yeah, so let's get started. I'm very happy to have Professor Tom Broadhurst from the IPVAS Foundation and So Tom is also our visiting scholar, and he has been working with many of us over the almost 2 decades at the science year event. So we worked a lot on the Hubble Space Telescope microsite treasury program, Flash. He also had a very important contribution to the development of the wave dark matter, the cosmology. It's also known as a particle dark matter. Today, I'm going to talk about very fresh results coming out of this JWST observation of the galaxy cluster deep fields. Yeah. So let's welcome Tom.
Well, thank you, Keiji. It's an absolute pleasure to be back after this interruption for the last few years and see many of the familiar faces here. So not too many casualties. Although poor Zihong, he's not doing so great. So I see him hopefully during this visit, but Justin may show up. He's been teaching us. So most of this work is in fact originated here in Taipei, sort of building on the lensing side with Keiichi, and then with my interest in the amazing simulations that Zihong and his team have been pioneering here, first to make these kinds of simulations. I mean, presumably many of you will be aware by now that this idea wasn't just a kind of flash in the pan, but has picked up and become at least as viable as standard CDM because of its simplicity and the way it matches well, in particular with solving some of the main problems for cold dark matter. And it is a form of cold dark matter. It's extremely cold condensate, bosons in the ground state. And Zihong had this sort of vision that this would in fact be viable as dark matter, and figured out how, along with Justin in his code, to simulate this. It's very difficult. It's not like embodied. It's a wave, so you need to do it on a grid. Although the concept is simple, the application was so difficult that Justin and Zihong, they had to build their own GPU computers to do this back in 2013 is when we started this. So and then we've been testing the predictions of this. This is unlike the usual simulations, where you get out what you put in. Here, what we got out was something that we didn't put in, which is all this standing wave behavior in the nonlinear regime, which surprised us until we realized what these waves were. And of course, it's an interference pattern, but with a soliton in the ground state in the middle. That's over there in the middle. I don't know if I have a. Is this a. No idea.
No idea.
Right. So you see this dense object in the center. That's going to be the focus of much of this talk, because many of these distinguishing predictions relate to the existence of this necessary existence of this overdense core. It's not a core in the usual sense of something smooth, but it's actually overdense. It's a standing wave. Right. And then I'll talk about how this relates to our interest in binary black holes, constraints on primordial black hole dark matter, and comparisons with that as perhaps the main competition inspired by LIGO. So we'll see if we get to that. But let me just start by saying that all this work involves these two guys here, and also my student in Bilbao, and now this team in Arizona, the Pearls team, where we have the first results from JWST. So it's quite exciting to see the new data, spectroscopy included. Okay, so just a quick motivation, going back to the legendary Nick Kaiser, who was the first to make use of this, what's called the Schrödinger-Poisson coupled equation, as an approximation to the clustering of dark matter. And since then, the motivation has grown in terms of this axiverse picture, which is that light bosons spanning perhaps small galaxies appearing in these filaments. And when you iterate this equation instead, putting in this non-relativistic potential here into the Schrödinger equation, you find the same large-scale pattern emerges, but there's an absence of small galaxies. And that's because there's a kind of a gene scale built in to this, where you can't confine the material on a scale smaller than the de Broglie wavelength. And we'll see this de Broglie wavelength appear in a moment. Here you zoom in on one piece of it, you'll notice that there's these waves occur. So yeah, that one shows our original paper on physics nature there. And then you can notice that in terms of the phase of the wave function, it's the de Broglie scale is obvious now, and it's, you know, larger wavelength in low density regions where momentum is low, and within galaxies. So if you square the wave function here, you have the mass distribution. So you can identify these halos as galaxies. You see that the de Broglie scale is much finer. It's much harder work. The waves are changing faster, interfering on a smaller scale, and so this is very demanding in terms of the time scale required. You might have prepared this slide. Does it look familiar? Somebody did. It's not one of mine. It looks very nice. Just to let you know, in case you think. So here's how Justin managed to achieve these simulations by use of an adaptive mesh. Right, so that's been crucial in not only achieving this simulation but maintaining our lead in this because no one else has yet managed to implement an adaptive mesh. And so very quickly, as your simulation evolves to lower redshift and the scale becomes much bigger, then you need to refine and refine in order not to run out of steam in your simulation. So what happens initially is everything looks very smooth, then these filaments appear, and then these galaxies become clearly defined. So very smooth beginnings. That's because there's no small scale structure below this kind of de Broglie scale, which does depend on momentum, so it's not a particularly well defined scale. And you can see here in detailed comparison with CDM, Gadget 2, and Z-Home simulation, there's complete absence of all these little galaxies. So early on, we expect to see an absence of small galaxies. When galaxies first form, with CDM, that will be much higher redshift and there will be far more of them. Now, let me also mention very distinctive behavior within galaxies that's predicted here. You see, the smaller the galaxy, the wider is the core. The core, if you zoom in, you always see this soliton. In this case, that's this massive galaxy here. You see that the core width is, maybe less than a kiloparsec. Here is several kiloparsecs for this dwarf here, for example. That's because the momentum is lower, and so the wavelength at the de Broglie scale, which is just given by the momentum, so it's the boson mass times the typical velocity. Typical velocity in a low mass galaxy is smaller, and therefore the wavelength is much larger. So that's very distinctive behavior. It's unlike the behavior you might expect in any kind of normal or any kind of other kind of dark matter that we've seen discussed, where the bigger the galaxy, the bigger would be any kind of core. For example, in self-interacting dark matter, you expect a scaling that way. Here, the scaling goes the other way, and that's very testable. And here's excuse me, one of the sort of a toy model where Justin explored the relationship between the core behavior and the halo. So the core halo relation depends, as I say, on not only on the momentum, on the mass, but there's this scaling that we needed to investigate, and so that provides another testable prediction. Now you see here, look, I just wanted to show off a bit. this idea began, it quickly took off. This is a prediction that we can make for this year. So it is not going away at all. Some people prefer it would, but we're a bit surprised that, in fact, it's catching on well. And I think one of the reasons for that is it does provide a viable, testable, simple alternative to heavy particle dark matter. What CDM and, in other words, heavy particle dark matter share is that they're both, this is non-relativistic. So there's only gravity, but the wave behavior means that there's this fixed, this dependence on a scale, this de Broglie scale, which you can then tune and examine to try and solve all your problems that plague CDM. So as we've shown that those problems can be fixed, and in the absence of any heavy dark matter particle, is actually becoming more and more of interest to, and there's a lot of papers now that build on this. Right, I'll show you that. In fact, you don't have to just take our word for it. There's some very smart people here in Harvard who have basically confirmed our predictions, and they've included some baryons. I'll be using their simulations as well in making some tests shortly. But basically, subsequently they showed that indeed, in terms of their best calculations, we were all in agreement on what these predictions are. So the Hernquist group, very well known for its n-body dynamics. So one of the things that you should look out for is an absence of high redshift galaxies relative to CDM. So you can see here, you go back in redshift, CDM, lots of tiny little galaxies. With wave dark matter, we see, well, this is just one filament, but in the volume that we simulated, it's about 30 megaparsecs on a side, the maximum volume. There was the highest redshift galaxy formed at redshift 13 for the boson mass of interest, which is
5 megaparsec by just modifying the spectrum with particles, or really
this is a real simulation. This is definitely from
5 megaparsec. Oh, that's good.
How good?
You said the simulation box is 5 megaparsec.
Oh, the original box. Yeah, I think that. Yeah, that was. I can't quite remember, but it's about that. Yeah. That was the first simulation that was really. Okay, so you can see that there's an era where there's only smooth filaments with wave diametrics. This is the symbol I'm using. So you know, now it's possible that stars and gas form in these filaments. Gas can cool and form stars, apparently, according to these simulations done in Harvard. I'll look at that a bit more. Whereas CDM, you'll always find something smaller and smaller as you go back. There's a scale-free continuity, so there's no particular era here. Whereas for wave diametric, it takes a while before the galaxies will form. And so it was sort of interesting that in our early work with Keiichi, we had only 2 high redshift galaxies, and we were wondering, you know, is there a shortage of lensed galaxies? So this was from the Clash survey. So when we were looking with these tremendous magnifications, we should see, you know, everything out there. We're limited by the optical, you know, the fact there's not much infrared coverage with Hubble. So we were not sure whether there's really a shortage. We only found 2 high Z galaxies in all the work that we did. And it turns out that with JWST, with all that infrared extra coverage, there aren't that many more. So here's our JWST image of this same galaxy. So you see the improvement in terms of image quality. Right, it's kind of a double system. So around the Einstein ring, highly magnified, and much more clear. But what's amazing is the spectrum, here we go. This one, you see there. Now we have a really nice spectrum. This is from the team actually with Dan Coe. So that we just published that earlier in the year. Because it's the Cosmic Spring team. Yeah, I should have mentioned that before. You know, this is, you see the quality of JWST in terms of the, you know, there's no detectable flux below the Lyman break. Well, below Lyman alpha, in fact. An absence here. That's this wing scattering effect. And then all these helpful emission lines that appear right at the limits of the data at 5 microns. So this is a really fabulous spectrum of that thing, confirming. But you notice the redshift actually is not quite as high as we thought. And that's been true of nearly all these cases. The photos he estimates tend to overestimate the real redshift by around about 10% when they're correct. And it's just a weighting effect, I think. Now we understand why this is happening, but it turns out it's systematically the photos is overestimate, and that's just because of the flat prior that was used, whereas of course the number density with redshift dropping very rapidly, it would have been more sensible to weight things with that steep prior to get a more accurate photo Z. So these were kind of unweighted, and they come in a little bit low, like 10.2 is the redshift of that system. Then we found accidentally another one, 3 image system. This is completely serendipitous. We were looking for a transient event, and we put some slits on this tiny red system here. You can see there are 3 images of it. And that turned out to have, you know, kind of very low signal to noise break there. You might or might not believe. But very helpful emission lines right at the far end here, is oxygen 3 HPT. So those nebula lines really make it very clear. You can see them here. So this is very deep data, and yet you know, we could have seen things at much higher redshift, and we see only this one, 9.5, redshift to 9.5. So that we just published that, and then we have another one, which 3 image system here, so A, B, and C, and this turned out was even worse in terms of signal to noise, but But the break is clearly believable, and that turned out to be 9.8 basically. That's the slit there with JWST. Very, very faint thing. Now this object was already known to us from our earlier work with Clash Survey. That's the one that Addy and I discovered in 2000.
This is not Clash, but from the field.
A, B, and C. Is it?
Name of class is different.
There's not a Clash.
Hubble field.
Okay, frontier fields, yeah. So anyway, it's from the fact that we discovered this in about 2018, right? Remember that? You don't remember that? With Andy? I thought you were included. Anyway, never mind. But anyway, with various slits put on various objects, this one came out to be the highest redshift thing. So it's not a new discovery, in fact. So there's only these few high Z objects in all the clusters that we've imaged deeply with JWST to date. So there's about maybe 8 clusters that we've done very deeply with Dan's team and with Roger Windhorst's team, the Pearl's team. And you see these things are very small in the source plane, just a few, maybe 100 parsecs in scale. This one, because of the magnification, you can see extremely low luminosity. This is a dwarf. These are field galaxies that have redshifts. So these are all spectroscopically comparison. You see that there's one there, 11.1, from the wide field searches. That's the object discovered by Richard Bannons over a very wide area. So it's really clear that there is a deficit of high redshift galaxies, I would say. Now you've probably heard a lot about luminous high Z claims, most of which have gone away. It seems now, on pruning the data, that this field team are finding a kind of, a transition, if you like, maybe 11.5. Well, most of these are photo Z's, so it's still likely that they're overestimated by at least 10%. Some of them will be catastrophically wrong, probably this one. So let's not get too excited yet about those high redshift claims based only on photo Z. Now, if we ask, well, this is still very early days, right? We're just writing this, put in these new redshifts for these lens systems, and we're effectively working at 31st magnitude because of the magnification. And you see that with CDM, just a standard extrapolation of the count models that you predict maybe an overall a factor of a few at least, maybe an order of magnitude more than are detected. So these are these 4 objects, right? And you see that there's an excess predicted for CDM here. And this is based on this Galform modeling by postdoc Giorgio Manzoni. He's working with me and George Smoot and Jeremy Lim in Hong Kong. And we've just been, putting together what we have in terms of reliable spectroscopy and number density. We need to know the lensed area and all those corrections. And we see that we'd like something a little bit more massive than 10 to the minus 22. Maybe just 2 by 10 to the minus 22 would already match this number. Although there's more data coming, but it's at a very slow rate. There are just very few of these high redshift galaxies, despite the fact that the data is certainly deep enough that you could, with 31st magnitude with lensing, you should detect a lot of tiny lensed galaxies if indeed the CDM picture is correct, that scale free from initial conditions. So these are the first claims, and not to be taken entirely seriously yet, but we do have confidence in the lens models. These are lenses that we've studied for a long time, been well pinned down by our strong lensing work, with the frontier fields and the clash clusters. So we know how much magnification we have everywhere in the field, and yet we don't find many high Z galaxies. So keep an eye on this. Another thing to look at is the morphologies of these lensed galaxies. And I'm going to come back to this, but many of them have these compact cores and diffuse behavior, and that is interesting in terms of the wave dark matter picture, that these lensed dwarf galaxies of fairly high redshift. These are not the highest redshift, but high enough that you can resolve them well now with JWST. So I'm going to come back to that. Here's one that was a Nature paper by another group, Jade's group, and they have this core and this kind of extended halo, and this thing's at redshift 7.4. They made quite an interesting story out of this being an inside-out galaxy, that the stars in this core are older, they form first compared to the halo. That is kind of interesting, as we'll see. So just let me mention that. Now, in terms of lensing effects, the granularity of these halos is an interference effect, provides a very distinctive prediction for the Einstein ring, which will not be smooth for a galaxy comprising this kind of interference pattern. And this may be another slide that you made, occasionally. It's very beautiful. Yeah, you can make all my slides. I think you must have given that to me. It's better than I can do.
Yeah, I think I was talking about this.
You must have given the talk. Yeah. We've all been leveraging these wonderful simulations. Now, you can notice that with that, if you just ask what's the magnification pattern for this type of interfering dark matter, see there's a kind of corrugation everywhere. You will have small distortions locally, quite unlike a CDM. So this is again from Justin, student James Chan. You might remember James. He's in New York now. He was here, student of Justin and Zihong. And this one predicted that there would be local perturbations to the magnifications of quasars. You may be aware there's a strict relationship between the magnifications of these two images and this one. So when you have a close triple, the outer pair equal the brightness of the inner one. And they should do by just because it's an elliptical geometry. So that's a well-known requirement of lensing, and nearly always that is not what's observed. They're usually at least 30% off, sometimes off by a factor of 20. That's been a big puzzle. It's called the flux anomaly problem. So this was addressed in this paper, and you can see, for example, here that if there's an 8 for CDM, because it's not entirely smooth. It looks smooth to the eye, but there's a slight 8% deviation. 0 would represent a perfect ellipse in terms of this magnification ratio. So you should expect maybe few percent level variation in brightness. Instead, with wave dark matter, you get 40%, much larger, and that's because you can see the critical curve can locally affect each image. So then, therefore, you're adding a kind of a noise to this relationship. Now, this illustrates it quite well. This is from James, and you can see, wave dark matter and CDM. If you compare smooth and prediction, where the images would fall in this kind of brown color, compared with blue, you see there's always an offset. They basically track each other. Sometimes you get an extra image with wave dark matter, just occasionally you may see extra ones pop up here. But in this case, we're just moving the source around randomly in the middle to simulate different lenses statistically. And so that tells you, that's about the level that you expect. And if you notice that the wavelength of these corrugations is about the de Broglie scale. So that's what gives you the offset in the image positions. So not only should the brightnesses vary, but the position should be offset as well. And so we made an effort to measure this effect in terms of the positional offsets. Because you might always argue with brightness, the quasars varying in brightness, perhaps somehow but with positions you can be, some of them are very accurately known, particularly in the radio. And with another student in Hong Kong, Jeremy, also Zihong and Justin here, we just published this recently. You can see the complexities that are caused by these wriggles, and the critical curve for a massive lensing galaxy, like I'm going to show you now, we analyze with this, are really, there are islands as well. You see that on the out, so that would be a normal Einstein ring going around here somewhere. And so you can see that even quite offset from the Einstein ring, there are going to be, the positions are going to be affected and the brightness is affected. On the inside, negative overdensities, so these are corrugations, this is I should say the deviation from the mean. The density is rising towards the center, but these are the wave dark matter type deviations at the 10% level. So you have to project all that with lensing, and so the effect is small, but the scale is preserved. That's the great thing about this. Even though lensing only refers to projected quantities, the de Broglie scale that you'd like to measure, because that gives you the boson mass, is unaffected by the projection, because this is just a stochastic. You see that we figured out how to calculate the variance, and it's very much like the CMB. The CMB fluctuations, and then you project it through it, and that allowed us to make convenient statistical realizations without the need for simulation. Just because this is when you have a large enough object with lots of granules, you can use this, basically rely on the central limit theorem for a kind of stochastic process like that. There's a little bit of complication in that the stars in the lens will act as additional lensing mass, but smooth compared with the dark matter. So you need to be able to see the lensing galaxy and figure out what's the proportion of stars, stellar mass, to dark matter. And that changes the amplitude of the corrugations, well, not the wavelength, as you will cross here. So that will be a smooth lens, pure dark matter, 50% dark matter, 100%, 90% dark matter. Stars, 10% dark matter. These wriggles are always there, but they will be low amplitude. So that's a correction that needs to be made. So then we applied that to this radio lens, where there had been a long recognized problem of positional anomalies. No smooth lens was able to account for the locations of these components within the radio structure, which appear in 4 different images. It's a bit complicated here. You can see that there's 4, even here. So the ones that are close. So basically, no smooth model will work. And this has been a point made by these guys for a long time. And then here's one realization, for example, what wave dark matter would do with the correction made for the stellar light. And you see that you sort of scatter the images statistically over a wide range, quite easily able to account for the observed positions of these images. So it was a bit hard to see, but anyway, you take it from me. All that corrugation means that it does indeed quite well match from that. Anyway, so that was the point of that paper there. That we applied this approach, and we claim it does indeed statistically account. You could spend all the years and years CPU trying to find an exact match, right? Because only one realization will work, but statistically it works. Right. So
given this parameter, like a dispersion of this perturbation, degree of perturbation, and you run multiple simulation to find the best fitting.
We're not fitting the individual data. We're asking, do the deviations from a smooth model match what you expect? And then we have a range of parameters for the model, like the de Broglie scale, the fraction of stars, we vary those within limits. And we find indeed that it does.
How many systems do you analyze?
This one. Yeah, just this one. Yeah. There are others you could look at, like for example this one. I think you can just see by eye that this works. And other ALMA experts, and one of the things that I would really like to do around here is to ask, find out how much faith one should have in these small brightness peaks. Because with lensing, you could take all of this and you can reproduce most of that. And vice versa, you can take all of this, de-lens it, re-lens it, produce this, and this. But you'll find that all the brightnesses are slightly different. And the question is that the symptom of wave dark matter, or is it just the data can't be trusted? I have no real feeling for the quality of this, but this lens was well studied here in Taiwan, I think, by what's her name, Sherry Soyu. They've been modelling that one.
You cannot trust the counting appearance.
Sorry?
You cannot trust it.
Can you trust it?
Phase error.
Yeah, but some of it was trustable, presumably, right? For example, the fact that there's more flux here than here, right? So the question is, is that trustable, that peak there? You could use that because it should map onto something like that over there. Or maybe also here. You could identify where these things are and then ask. So I would really like to quantify that. I think that this crucial data for answering this question, because you need a source with a lot of small scale structure and you need it to be well resolved, and then you can ask whether there's a need for a non-smooth lens like this. Okay. All right, so as I said, the main issue is whether or not galaxies, especially dark matter dominated galaxies like these dwarfs, do they host a distinctive core or not? And in our first paper with Zihong and Justin, we focused on this fornax cluster, and we derived the boson mass from this core size that was reported there for fornax, and that has been a long puzzle for the dwarf, for CDM, right? Because these such cores have to be explained by non-dark matter means. In other words, outflows and so on. And I don't know if any of you already believe any of that, but the problem with that is that you keep blowing stuff out with gas and attempt to reduce the density in the center, you'll increase the metallicity of the recycled gas and therefore the stars that remain. And these things often, some of them have multiple populations, some of them don't. And even if they do, they're not very metal rich. So you know, it's never been clear whether that could work. In any case, the exploration of cores has always been limited to a smooth plumber-like model, you know, where the dark matter sort of rising up like CDM would have this kind of. And so with wave dark matter, the core is distinct, it's a prominent overdensity. So we just did the simplest thing, looking at the star counts of all the available high quality data for these dwarfs with my student in Spain. And you can see that, you know, in nearly all cases, so here's the log scale, so you see the core better. And the linear scale, so you can see this halo. It's kind of tantalizing, you know. Here's 3 cases. There's lots of cases. Here's a whole bunch more. I would say that it does appear to be a kind of break in the counts from sharp, you know, what looks like very much like a soliton. So the soliton has a very distinctive profile that is only the boson mass sets the scale of the soliton. The shape is actually independent of the boson mass, only the scale length. So there's no real free parameter there. And it matches very well these star counts in nearly all these cases. So we just looked at whole sculptor, you see, and then there's been a lot of reports about extended halos, and is that consistent with the idea of tidal stripping, since many of these orbit our galaxy. And that becomes that's been you know, something natural in this context. You have these wide halos, these cores. In Andromeda, you see similar behavior. You can see that there's this kind of break feature. So you have a core and a halo. If you just fit the halo, it would underestimate the core. If you just fit a plumber model, the usual plumber model, they kind of fit reasonably well, but it definitely falls short in the halo region. Whereas the soliton is a really nice fit in nearly all these cases. So we didn't really see any exception. Also, the dispersion profiles, the velocity dispersion against radius, these are all very well studied examples, and you can see that the prediction is kind of consistent with that. Dispersion is predicted to peak at the core radius because you have more interior mass, and then drop beyond that because the density is dropping down. And this data is sort of reasonably consistent with that, although, you know, you could argue it's pretty flat, but that's just a consistency check. It's no, if you ask, well, you know, take the profile, what would you need to, and then you have no free parameter at that point, well, just a small amount, and then you can say, well, does it fit the dispersion data? And indeed, it does fit it very well. Unfortunately, the dispersion profiles are not very distinctive, so it's they're not that useful as a matter of fact. They're good for normalization to get the total mass. Now, the other thing that Justin and Zihong and I predicted is that tidal stripping will reduce the halos for those dwarfs orbiting the Milky Way very much more than the core. The core is kind of self-reinforcing. There has to be a ground state. So unless you totally disrupt the core in some catastrophic situation, you always end up with preserving the core but losing the halo as time goes on. You see from the initial. So the more this thing orbits the Milky Way, the more loss there is of this halo. So then we can ask, well, if we go back to this data and we look at radius from the Milky Way here, you see there's a whole bunch that are quite nearby, and then there's some that are well beyond the virial radius of the Milky Way. I showed you those before, these blue ones. You can see, I think, that the ones that are further away have a shallower break than those that have been orbiting the Milky Way. So you see the shape here is all pretty much the same, and then you have this kind of drop there. And then if we compare that with these predictions, you could say, well, you know, these isolated dwarfs that are in the local group, but they're not orbiting the Milky Way, on average, they have this behavior, and then the orbiting dwarfs, the same similar size soliton. You can see the scale radius is the same, but the halo is much reduced at sort of level that would be consistent with a few gigayears of stripping. So we quite like that. And then we asked, well, what about these ultra faint dwarfs? And that's really tricky because they are so small, about 10% the size of the typical dwarf spheroid. And now there's about 30 of them known, at least, orbiting our galaxy. Like this one here. You see, compared with Fornax, it's really a tiny thing. But when you look at all their profiles and add them up, so here's the Milky Way ultra faint dwarfs, you can see also this kind of core halo structure. So again, a log plot, here's a linear plot. Here's the dwarf spheroidals, but for comparison, you see the scale length here, maybe nearly a kiloparsec. Here is a tenth of a kiloparsec. This is the scale is different. So these are much smaller. And the dispersions, though, are kind of comparable. The same story for the Andromeda dwarfs. The dwarf spheroidals are very similar to the Milky Way, as are the dwarf spheroidals, the ultra faint dwarfs. They're very small. And the same story there. So that's a bit strange. You need a much higher boson mass, about a factor of 10 higher, to match these and to match these. Right? So if you say, well, all these dwarfs, dark matter dominated, you cannot match them with one boson mass. In fact, they look like this. So if you plot the density against the radius, and then to get the density, we just did a very simple thing, which is taken the velocity dispersion and divided by the core radius. That gives you a density when you square it. And that the ultra faints are low luminosity here, you see. They fall on this line, and this is where the dwarf spheroidals lie, Fornax and all the others are along here, including actually the Milky Way. I might mention that. So normal galaxies are here, and these ultra faints are representing a small number of galaxies, but they do not fit in with this picture at all. There's other ways of plotting that. But the point is that we're happy then to invoke this axiverse picture. We have multiple axions, axion being a boson. And with a difference here of about a factor of 20 in terms of the in terms of the mass ratio. So if indeed these ultra faint dwarfs, if you regard them as real galaxies, and there are good arguments for that, then our light boson picture needs modifying. You need to add another boson at least, but you can do it. What's interesting is that this slope here is -4. I should have said that, but that is the unique prediction for wave dark matter, because as you go to lower density objects, the momentum is lower, the radius of the core is larger. So that's why it behaves like that. For CDM, you get a very different behavior, almost orthogonal. Orthogonal behavior. The larger the galaxy, the higher the momentum, and so this is exactly what this -4 slope is what you look for as a prediction, but you need two different axioms to match that. Okay, so that's maybe a weakness of this thing, or you could argue, well, here the axiverse is generic, and then you would embrace string theory even more strongly, or at all, depending whether you embrace string theory. Some people don't like it, but anyway. The other thing you can ask is, well, why are these dwarfs round? In the WaveDM picture, they would not have merged very much. Can we explain the roundness? If all those stars that you see there were born in a disk, you would expect that there would be a disk there. But what happens in this, interestingly, in this, I think Justin and Zihong have also been looking into this, is that the orbits of the stars are scattered by this interfering density distribution. It's not the interference, it's the variation in density from place to place. Because the interference goes from being totally destructive to constructive. So you have a mean plus or minus the mean. That's quite a range in density. That means any star that might initially have been formed in a cooled gas disk would orbit in a progressively more random way over time. And it gets kicked by these perturbations. And so we've actually been had this idea that, well, maybe that's what makes these things round. In fact, they're not exactly round, they're oblate spheroids, meaning, two of the axes are similar and one is smaller. So when you look at the distribution of stars in these dwarfs, you see that they are in fact sort of not flattish, but not perfect spheres. Spheroidal, but oblate. And if you do start with a disk, there's different ways you could begin these simulations, but if you start with stars in the disk and you follow it over time, you see that over time the core radius becomes larger. The thing remains sort of oblate. You can see that there it's 10 gig years, only 3, and then that's initially 1 gig year. But there's still some memory of the rotation. So, because it's not entirely smoothed away, you can notice that if a disk had, say, plus or minus 10 kilometers a second, so a low mass dwarf galaxy, over time, you would still see 1 or 2 kilometers a second net rotation, and this has been claimed, in fact. I was looking into this and thinking, well, that won't work, but there are some papers, I don't know if I've referenced them there, where recently were claiming that this kind of level of 1 or 2 kilometers a second from one side to another is in fact present in the data for some of these dwarfs.
So, this from this self-consistent simulation, you have this wave dark matter and also
particles, yeah.
So there's also
the test particles. Just treat them as test particles.
So there's no reaction to the dark matter.
No, because the dark matter dominated, so you don't need to worry about the mass of the stars. Okay. So that's a very intriguing thing, right? It can maybe all dwarf galaxies, in fact, become round over time through this process. Now, others have applied this scattering process. Jerry Oestreicher and Scott Tremaine have independently papers on the thickening of the galactic disk locally, because locally, you see the stars, the young stars have a small scale height in the plane, and then the older stars is a kind of almost a square root behavior with time that looks like a random walk. So they've been making detailed calculation. Oestreicher has been claiming that there is consistency. In fact, it can explain the age thickness relation for the Milky Way stars in the solar neighborhood, which has been an interesting puzzle. So this is the same kind of calculation, but with an idea of actually quite radically explaining these dwarfs as becoming round through internal relaxation. And with the advantage that, you know, you can then start from a disk, because you ask, well, how do these things form? So we actually now have been looking at some of the simulations from the Harvard group. And I'll come back to this motion of the solitons shortly. What am I going to say about that? Yeah, look, this is a very nice paper, mock set down. It's the one that I mentioned before from the Harvard group, and they compare CDM with warm dark matter and wave dark matter. And you see warm and wave, they have these smooth filaments because of the lack of small scale structure. So for example here, gold and matter. And they've included gas and stars. The gas is included self-consistently, hydrodynamically, as best they can, and then the stars are then tied with some scheme, you know, the Schmidt law to the density of the gas. So with that caveat in mind, you could then look at the distribution of the stars and ask, how does that compare with what we see? And this is very exciting. This just came up a couple of weeks ago. We got this new data, one of the fields on the side of the clusters there. An incredibly deep image of this dwarf galaxy was noticed. It's actually only at a distance of about 40 megaparsecs. Even though it's not local to the Milky Way, and many of the dwarf stars, it's actually deeper because it's JWST. You can notice this thing. Well, it has a core of about the same as Fornax and those other dwarf spheroids, about half a kiloparsec. But notice it's not symmetric. That's the interesting thing. Why does this core? So if you imagine a soliton, what you maybe want to look for is this motion of the soliton that moves around within. So if you look at those simulations, you can see all the time the soliton is moving around on a time scale. There's only one time scale, which is the de Broglie scale divided by the mean velocity, or the velocity dispersion. So if you took that to be about half a kiloparsec, dispersion of about 10 kilometers a second, you come up with a time scale of about 10 to the 7 years, so quite a bit less than the Hubble time. And so if you look in the simulations, you can notice this thing moving around all the time. And it moves around on a scale about equal to the de Broglie scale. So about the size of the core. So the core is set by the de Broglie scale, and it moves around like that. Sort of leaps about a bit. Just didn't notice this, and we have this nice paper all about that recently. And then looking at this, I thought, well, maybe this offset here, the fact that it's not centered, why would it not be centered? It's just some smooth ball. In fact, you see here, look at warm dark matter or cold dark matter, simulated galaxies from this same, zoomed into here. Right? So these are their stars. Looking at the stars now. You see they're very symmetric. Whereas with wave dark matter, that's meant to be indicated here, as these three, you see there's an asymmetry there. This is caused by the stars trying to follow the soliton as it moves on a scale of about the de Broglie scale, about half a kiloparsec. The star's crossing time is comparable with the soliton shift, if you like. So, because the crossing time is also given by the size of the core divided by the speed of the stars, it's the same time scale. So the stars can have enough time as they cross the core to feel the change in the center of mass of the soliton in these simulations, and that's why this soliton is offset from the center here. So these are the predictions. You see this core is definitely offset, and the asymmetry very similar. Yeah, just compare this one with this one here. So I think that's a little bit exciting, because it surely betrays the presence of something moving dynamically within it. Fornax is maybe even better case, actually. We didn't look at this before, but if you look at all the stars in Fornax, there's main sequence and giants, and there's low and high metallicity. So, well, if you look at all of them together, you see the core is quite well defined. Maybe there's even a sort of a gap. The thing's leaping around so much, it could create temporarily, and a minimum. At least, I don't know. That's a bit fanciful, but we need to look at.
How many slides we have?
Oh, right. Is that the time? We finished. Yeah. Okay. Yeah. Don't worry about it. Anyway, okay. We also think we see a soliton in the core of the Milky Way. Okay. Just to let you know about that. Yeah. The ultimate test of this kind of wave dark matter, you should know that, is that because it's a scalar field, it oscillates on the Compton time scale, just given by the mass of the particle. This is not the de Broglie scale, much smaller by V over C than the de Broglie scale. And so pulsar, the timing of a clock in an oscillating potential like that will give you a residual, and that depends only on the mass of the boson. And the sensitivity is better where the density is higher. So when SKA is providing, millisecond pulsars in the center of the galaxy within this soliton region, which would be about 100 parsecs for our Milky Way. Remember, the momentum's higher, so the soliton is smaller and more massive. In that region, the clocks will be modulated on a time scale of months, just a few months. And we predict that is actually testable. And we've been doing, we look for it in this first date. Now, this is a claim detection. You might have seen that a couple of weeks ago from Nanograph. It does seem like the noise is going to be larger than we hoped. Right, so that's the Earth's orbit there, and timescale will be a bit smaller than that. That's 1 year, so we're talking about a third of a year for 10 to the minus 22. So you'll be looking for some peak here amongst all this claimed detection, which incidentally we have modelled with soliton black hole, but don't worry about that. There's a totally different story. But the point is that there's going to be a bit tough. You can't do this locally with the local pulsars because the density of dark matter locally is too low to detect that given this background, and the error, the noise on the background is what. But if you go to the center of the Milky Way, not the center, but within that 100 parsec region, where we reckon we do see evidence of a soliton of dark matter from the rising dispersion, then you can detect that. Becomes it depends. The detection of the signal depends on the density of the dark matter, as well as the boson. So that you can look forward to very definitive test of this whole idea. If this timescale monotonic feature appears corresponding to all these bosons oscillating together in a coherent way, right? Yeah, and that means that you can do that. I was going to talk about all these new stars that we found and all the rest of it, right? But I think maybe next week. Yeah, we've got lots of interesting discoveries with JWST. Sorry, I've already gone all the time. Here's one of them. Right? We found some of these distant stars that are magnified. whole load of these things have shown up, and that provides another very interesting test of dark matter. I recommend this new paper with Pearl's team. Some individual stars there. Another one here. He's come up, brighten up, right near the Einstein ring, but not quite on it, and that's the clue. Right, that's it then. I think. Okay.
Yeah, thank you. Okay, maybe a few quick questions.
So if you don't expect enough faint galaxies at very high redshift, are you going to get enough UV photon to reionize the universe?
Yeah, I mean, the luminous galaxies and the AGN can do that.
And the current study of the quasars and massive gas at high redshift, the conclusion is that they cannot produce enough photons. And reionization has to come from much larger number of faint galaxies.
Yeah, I would say that you shouldn't rely on them. Yeah. They may be absent. Yeah. Now we did do a calculation of that with Zhihong, and I don't have it here. But you remember that the optical depth to Thomson scattering was dropped to like 5% with Planck after those WMAP early claims when the reionization was supposed to be 17%. And then we could understand that, well, if with this late forming, that would match quite well. So I'm not quite sure quantitatively how much I agree with you on that one, because I remember that the sort of effective redshift of formation would be around 7 or 8 to match the 5% optical depth from Thomson scattering. And we did do a careful simulation of that. In one of the we have 3 papers about. One of them is all about that subject actually, and we thought was good, you know, and that so everything that went into it, including the absence of high Z. So, you know, it doesn't take long before a lot of galaxies do form, and it all depends on the boson mass. And this is the plot to look out for at the beginning here. You see, by a redshift of 8, there's nothing there, right, from eyes. You get just a few bright things. But if you look then at CDM and WaveDM matter, all the luminous ionizing, you know, I don't know how much these small things will contribute, but suddenly there's not much difference in terms of luminous galaxies.
So you need to push the reionization error to a very narrow range.
Well, you want it later. You just want it later, and I think later was argued for because the optical depth is low. But AGN, well, it was claimed by my dad. Remember they had a new paper about that. Could explain all of that without much need for any. But that was just his. I don't know. Yeah. I mean, I don't think he's going to be pushing the limits too much.
So you show that this asymmetric profile predicting wave dark matter compared to JWST observation.
Well, the one for that dwarf galaxy.
Yeah. You show the very data part. And so this simulation for dark matter or from hydro simulation?
This is dark matter and hydro for 3 cases. That's wave dark matter, warm dark matter, CDM. And these are just different X, Y, and Z projections.
Sure, but is it the profile of dark matter or gas?
The stars.
It's stars.
Yeah.
Okay, so you try to compare to the JWST.
Yeah, exactly. Yeah, that's why I was comparing it, because thankfully they have done the relevant calculation. And so this kind of asymmetry here is very encouraging. Yeah.
Oh, okay. I thought it's dark matter only.
Yeah.
Okay, it's very encouraging.
Yeah.
Good.
Okay. Thank you. So the Tom Gab is staying in ASIAA by I think August 9.
That's
yeah,
right,
yeah,
9.
Yeah, staying in my office 19. So I encourage you to talk to him and more excited here. He couldn't finish all the talks.
Yeah, sorry about that. I don't know what happened.
Yeah, he's yeah. So let's start again.